For the last decade, scaling renewable energy meant covering massive stretches of land with passive fields of silicon. We built these utility-scale projects with a mindset that treated solar generation as a variable weather event. The sun shines, the power flows, and the broader electrical grid is forced to react to the influx. But that passive approach is hitting a hard physical limit. The single-junction silicon panels we rely on are reaching their theoretical maximum efficiency, the Shockley quasar. At the same time, we are running into a severe infrastructural bottleneck. As regions push toward 80 or 90% renewable penetration, the grid loses the physical stabilizing inertia that old spinning fossil fuel turbines once provided. The immediate consequence is waste. Right now, staggering amounts of midday solar generation are being curtailed or turned off entirely, because the grid cannot absorb the spikes. Continuing to build more of these passive arrays will eventually overwhelm the existing transmission infrastructure. To hit a terawatt scale by 2030, a solar plant must move from a passive participant to an active controller of the grid. To see how this works, we can look at a 2030 utility-scale project operating in a high irradiance environment, like the Pilbara region of Western Australia. This facility functions as a software-defined, highly dispatchable power block rather than a traditional farm. The first major hardware upgrade driving this change is the commercial rollout of Perovskite-Silicon tandem cells. This breakthrough relies on layering materials. By placing perovskite directly over a silicon base, the panel captures a wider spectrum of sunlight. The top layer absorbs the short wavelength rays, while the longer wavelength energy passes through to be captured by the bottom layer. This multi-layer approach breaks the old efficiency ceiling, pushing module performance from the low 20s to well over 30%. Physically, this means operators extract 30% more power from the exact same acreage and racking infrastructure used in previous designs. By densifying the power output without expanding the land footprint, the levelized cost of energy drops significantly. However, dumping that massive surge of raw generation directly onto the grid at noon is technically unfeasible without a way to capture and regulate the flow. By 2030, building a utility solar project without an integrated battery system is as obsolete as building a car without a fuel tank. For utility-scale daily cycling, lithium iron phosphate, or LFP, is the primary battery chemistry because of its thermal stability and cycle life. This chart shows the strategy operators use to avoid grid volatility. Instead of selling power during saturated midday hours, the plant eases storage to bypass the noon peak. The LFP battery array captures and stores up to 60. An overarching AI engine sits above this hardware, analyzing merchant market volatility to autonomously decide when to route power to batteries, when to sell, and when to provide grid stabilization. This software also manages physical upkeep. Using O&M 2.0 strategies, the system integrates thermal drone imaging and digital twins to manage hardware degradation before it impacts performance. These advanced software tools and grid-forming systems provide the necessary control to transform a field of glass into an integrated, grid-stabilizing asset. The macroeconomic reality of this shift is clear. These intelligent, hybrid merchant projects achieve higher internal rates of return than traditional flat-rate power agreements. But even with these grid-stabilizing tools, the physical electrical grid itself eventually becomes the bottleneck. Transformer lead times and congestion limits cannot always keep pace with the efficiency of the panels. By 2030, this leads to the construction of massive, behind-the-meter solar arrays, built entirely disconnected from the public electrical grid. These high-output dedicated arrays bypass the limitations of public infrastructure to provide a direct, continuous power feed for massive green hydrogen electrolyzers. By 2030, solar power becomes the primary physical feedstock for industrial production, decoupled from the limits of the electrical wires. Solar has moved beyond simply powering the grid. It is now the primary fuel of the industrial economy.